a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. Let's review basic terminology. If we have a square 1 foot by 1 foot, we usually refer to that as a square foot. And the area of this we will denote by the area 1 square foot. And usually is written in this way. We put an exponent of 2 on the unit of measure, and we read this 1 square foot. So if our square was a meter on each side, we would denote its area as 1 square meter. And thus we could have a square inch, a square mile, or any unit of length you wish. Squared would denote an area occupied by a square that large on each edge. Let's say we have a small tile floor using 1 foot squares, and we'd like to know how many of those 1 foot squares do we need in the entire tile floor. Well, we could just count them, but it'd be faster to count those on an edge, their lengths. So it'd be 1, 2, 3, 4, 5, 6, 7, 8. So the base is 8 feet long, and the height is 5 feet long. And then to find the total number of those squares, we would simply take the length times the width, which is 8 times 5, and get 40 such squares. And the number of those basic unit squares that are contained in this total area we call just that, the area. So the area, in a sense, is a count, if possible, of all of those basic unit squares. So we would call this 40 square feet is the area of this tile floor. Now, just as with circumference and perimeter, we can symbolize this relationship by the use of a formula. And we would have the formula statement that states the area is the length times the width. In our case, the length was 8 feet and the width was 5 feet. Now, multiplying their number parts, we get the 40, and multiplying the unit of measure parts, foot times foot, well, that's where the square comes from. Because remember, in our definition of exponent, when you're multiplying 2 of something, you can simply indicate it by this exponent 2. Now, we also need to note that this is the formula for the area of a rectangle. Different kinds of areas or different kinds of figures would need perhaps different formulas. For instance, if we wanted to know how many square feet tile are in this triangle, we could count some of them directly, but these on the edges are very difficult. We don't know what portion of this tile is kept in. So we ask ourselves, what is it about this triangle that we could measure or count? Well, we can measure the length of this base very easily. So that's 1, 2, 3, 4, 5, 6, 7, 8. So we'd say that the base is 8 feet long if each of these units of measures is a foot. It'd be difficult to measure the length of this side, but if we have a tape measure, we could. But here we can measure the distance from the bottom straight up to the top, which we will call the altitude, and denote by the letter H for height. And we can see that that's 1, 2, 3, 4, in this case, 5 even feet. So the two things we can measure is the height in feet and the base in feet. Well, is the height and base somehow related to area? And if we were to look in a math handbook, we would find there is such a formula for the area of a triangle. The area of a triangle is 1/2 times the length of the base, which in our case was 8 feet times the length of the height, which in our case was 5 feet. Now, multiplying the number parts, 1/2 times 8 is 4, times 5 is 20, and then foot times foot we denote by square feet, so we would say from the formula and our measurements that the area of this triangle is 20 square feet. And it's sure a lot easier to measure this, and then measure that, then multiply them times 1/2 than it is to try to count all of these and figure out what fractional parts do we have on these edges. That's the purpose of a formula. You see, the use of formulas like that help us to more conveniently think about the relationships and to more easily remember it. But its value goes well beyond that. Most importantly, formulas tell us how to get a desired result indirectly, which would otherwise be difficult, if not impossible. One could ask, where do the formulas come from? Well, experiment and verification is one source, but the more important sources are by using algebra, geometry, branch of mathematics called calculus, and another branch called trigonometry. One of their many functions is to derive logically formulas that people without the mathematics can use to get indirect measurements. For instance, if you wanted the area of a circle whose radius was 3.2 centimeters long. Now see, counting these outer rectangles would be very difficult. So we look in a math handbook which tells us that the formula for the area is pi, I'll use 3.14, times the radius, which is 3.2 quantity squared. So by reading the formula and knowing the order of operation, we can find this area with that one number. Now recall, from the order of operation we do exponents first, and an exponent of 2 means to take two of these and multiply them together, which gives us 10.24, and of course times the pi in front of it gives us an area of 32.2 square centimeters rounded to the nearest tenth of a square centimeter. Actually, here is a centimeter we didn't write in, and we perhaps should have. And you can see, not only am I squaring the 3.2 to get this, I'm squaring the centimeter to get just that, the squared centimeter. So see, by being able to have a formula, we can use minimal information and find indirectly something that is almost impossible to compute or count directly. That's the value of formulas. Now, where the formula came from, that's a matter for higher mathematics or experimentation. Now, the same formula book would say that the area of a square is simply the length of a side squared. That easy. Of course, that's because the width, which is the other side of this really rectangle, is the same. And see, length times width is side times side, which is side squared. So all we do is substitute the length of that side, which is 3, let's say, feet, and square it. So the square of 3 is 9, and the square of feet is square feet. So the area of this square is 9 square feet, of course, which in this simple case we can verify by actually counting. But in most application cases, it's complicated enough you can't count it. Here's another formula for the area of a parallelogram. Now, it's not a rectangle because I don't have right angles, but a parallelogram is in which the opposite sides are parallel. And you could prove in geometry that if the opposite sides are parallel, the sides opposite also happen to be equal to each other. Well, this formula says if you want the area, and again, see, we've got some difficult edges here. It's simply the product of the length of the base times the length of the height. Let's say these lengths are in meters. So we can see that the length is 1, 2, 3, 4, 5 meters, and the height is 1, 2, 3, 4 meters. So base times height. Multiplying the number part, and meter times meter we express as square meters. So the area of this parallelogram is 20 square meters. Now we wouldn't have to even see the squares. All we'd have to do is to have a tape measure, measure the base, measure the height, do what the formula tells me, and I have the area without ever even seeing it. Now if you have a four-sided figure in which only two sides are parallel, we refer to that as a trapezoid. And see, the formula for its area is a little bit more complicated. So let's read it and see what it's saying. It's saying it's going to first do inside parentheses by the order of operation. So it says to add those two things. Well, those are the lengths of the two parallel sides. It says take that sum times 1/2, and then that product times h, and h is the height between the two parallel sides measured on a perpendicular. So to find this area, we have 1/2, and we must now measure those two base lengths, and if we do, we find that they were, the upper one was 5.2 meters, the lower one was 8.7 meters. Now measuring the height, and we find that it was 4.0 meters. Now, using our order of operation, watch how we review what we've learned about measurement numbers. The order of operation says I have to do what's inside these parentheses first. And notice if I'm adding measurement numbers, they must be like measurement units. And this is meters and this is meters. If they weren't, I could not add. But since they are, I can add, and I get 13.9 meters. And I'll simply copy the rest of this over and get this rewritten expression. But now I would multiply the number parts and then the units. So meter times meter is square meters. In this case, it's easier to take 1/2 times 4, which is 2, and 2 times that gives me 8, 7, 2. So the area of that particular trapezoid is 27.8 meters, square meters. See, by now you should really begin to appreciate the use of variables, the use of formulas, the use of definitions, order of operation, and the units of measure and their rules, because all of that is what made this otherwise a very difficult, perhaps impossible problem to be simply a matter of simple arithmetic. Now these formulas go on and on. Every area of science and technology has its own handbook of formula, literally tens of thousands of them, written by experts to communicate to us how to do complicated things indirectly through easy measurements and the use of formulas. In practice, when working such problems as perimeters and areas, more than likely you will use a calculator to carry forth your arithmetic. So let's use this problem as a vehicle to show you a special use of many kinds of calculators. Once you determine that you are going to find an area, either you pluck from memory or from a formula handbook a formula for the area of this kind of a figure. In this case, we remember or find that the area of a square is the length of a side squared. So all we have to do is follow the instructions the formula itself is giving us. So this says the length of a side, which is 209.8 centimeters squared. And of course, if I square centimeters, it will be just that, square centimeters. But to square this number, Well, we know that squaring a number simply means to take that number times itself. And if nothing else, we can do that either by hand, or it'd be much more comfortable here to do it by the calculator. So let's follow that through. 209.8 times 209.8 equals. And we get 44016.04, or roughly 44,000 square centimeters. If this were a long number, it's a bit of a extra work, it seems, in order to have to write this number or enter this number twice. If this squaring is something that's done quite frequently, it would be nice if they could design a calculator somehow so that all I have to do is to enter this number once and push a special button, and it would do this part for me. After all, it's got this number in its memory already. Why not use it twice rather than us having to enter it ourselves? And with most calculators, that is exactly the case, particularly if your calculator is a scientific calculator, as this one is. Now, if you're curious whether your calculator is scientific or not, just look on it. Right up here, this one says scientific calculator. It will say so if it is. Some calculators that are not scientific will nevertheless still have a square key. So on your calculator, see if it has what we will call a square button. Usually it's indicated by an X with an exponent of 2, either written right on the key or just above the key. So let's zoom in a little bit closer to this, and perhaps you will see the square key on this particular calculator. There, that's a bit closer. Now see, in this case, there's the x squared written above this square root key. You should know about calculators by now this much, that if a character is written on the key, that means you push the key itself. If what you want it to do is written above the key, then pushing the key by itself won't do it. You must push a second key, which on most calculators is in this corner and usually says INV above it for inverse function. So when you push this button first, that alerts the calculator, in effect, that you don't want to do what's going on the key I'm going to push. You want to do what's above the key, and the calculator will do that. So on our particular problem, we wanted to square this number. So we would enter the 209.8 just once. Now push the, in my case, the inverse, this key, and that gets me to the square key, and sure enough, there is the answer just as I said it would be. So let's see, that's 44016.04. Let's write that down for reference, because I want to show you yet another way of doing the same thing. So if your calculator has a square key and you want to square a number, all you do is enter it once and hit the square key. Hit the key directly if it's written on the key, hit the corner key and this if it's written above the key. So you might check your calculator, see if it has that. If it doesn't, many calculators have yet another shortcut. There's yet another calculator shortcut that works on many calculators that are not scientific, as well as on scientific calculator. It's simply this: when you want to square a number, enter the number, which in our case is 209.8, but enter it just once, then simply hit the times key followed by the equals key without entering any second number or hitting any extra keys. Let's see if my calculator does that, and you might check that on your own calculator. Okay, this is suggesting that we hit 209.8. There it is. Now you simply hit the times and then the equal, and sure enough, there it is. So you might want to make a note of this for your calculator. First, recall that if you're trying to square a number, that this means you take two of those numbers and multiply them. And of course there's nothing wrong with that, but if you do this a whole lot, naturally we sort of desire a shortcut. So one of our shortcuts was to simply enter the number, then find the key that has the x squared either on it or above it. So you hit this number and this key, and that's all there is to it. So a number key and one key, unless the x squared was written above it, then you hit the corner key. And our second suggestion is if you don't have this, or sometimes this is just a trifle faster because you're so used to these two keys already, that you hit the number you want to square, then just simply hit times equals. You might want to try that on your calculator to see which it does, if not both of them. Always, though, if you're trying something new on the calculator, don't try it with a number whose answer you don't know. So my suggestion would be that you try it on a single digit squared, because you already know the answer is 49. So you can hit 7 times equal and check that you do get 49. Or hit 7 and then what you think is a square key, and again see if you really do get 49. That will save a fair amount of time in area problems. Let's use that fact on one more problem. Again, we want an area of a circle. So we check our handbook or our memory and we find the formula for the area of a circle is that number pi times the square of the radius. So simply doing as this formula directs us, we take the number pi, first determining how many places of accuracy is desired, and here I put in quite a few because I want to make a point in just a moment, showing how we can even do this fast. Then we want to multiply that times the square of the radius. And by the order of operations, I want to do this first, but we now know I can hit the number I wish to square. Then I have several shortcuts. I can either hit the square key, or I can hit the times equal if it does either one of these, and that gives me the answer directly. Then after doing whichever one of these I did, hit times, then the 3.1416. So on my calculator, 42.8, and I'll hit the times equal. There's the square. Then times again, but this time times pi. Then finally, to complete the work, hit the equal key. And I get that my area is 5754.9, and since the radius was in inches, inch times inch is square inches. Now I could just as well have hit 42.8, then the square key, then times 3.1416, then equal, and of course I'll get exactly the same results. But while you're looking at the calculator, you might note that most scientific calculators will indeed have a pi key, because that particular number is used a great amount of times. Usually it's not written on the key, it's written towards the bottom and written above a key. in my calculator is written right above this key right there, which means to get at that pi, you can barely see it from this magnification, I have to hit the corner key. So if I hit this corner key and then this key that I'm claiming pi is above, sure enough there is pi to quite a bit of accuracy, isn't it? So looking back at our last problem, it turns out it's not even necessary for me to write the number value for pi down on paper because it's already in my calculator. So now I hit the 42.8, and now I'll hit the square key, which remember was up here. So now it's squared. Now I hit the times, and I want the pi, but since it's above the key, I hit this, and then equal, and I get exactly my same answer. So you might wish to play with your calculator, see that how you can square and how you can use pi if it has it. If it doesn't, then of course you'd have to somehow remember the value of that pi. 3.141596 is more places of accuracy than you normally would use in most areas. Do you recall in the last lesson the key sentence we used to help remember this? There, that will give you pi to far more accuracy than you will need in most problems, even in a science. So if you can remember this very simple sentence and can count, you have pi. And of course there are certain basic formulas which are simply well to have memorized regarding area. Of course the rectangle, which is length times width, and sometimes referred to as base times height, depending your choice of nomenclature. And then its special case, the area of a square, and a generalized case that takes care of these two and a few more, the area of a parallelogram, base times height. And of course a rectangle is simply a special case of a parallelogram. And of course the area of a triangle, 1/2 the base times the height. And the trapezoid we had mentioned, 1/2 times the height times the sum of the two parallel sides called bases. Then finally the one we just finished, the area of a circle. This small group of formulas is used so frequently in future courses, both science and math, that's simply well to memorize it while you're working this lesson. And of course there are hundreds and hundreds of other formulas that are more specialized, which you would find in the appropriate handbook. This is your host, Bob Fennell. We'll see you at the next lesson.